So today we're going to do chapter 7, section 3, which is the structure of matter. The first thing we go over is the Thomson model of the atom, which is the old, wrong version of the atomic structure model, right? In this model, Thomson theorized that there was negative electrons, but these negative electrons were embedded inside this matrix of positive charge, like this. In much the same way seeds are embedded in a watermelon, right? And this sphere of positive charge was very low density, right? So there's a lot of things that we know is wrong with this model, right? First of all, the electrons are not orbiting. Second of all, there's no nucleus, right? The correct model later was improved by Rutherford. Of course, we know now this is the correct model where there's electrons orbiting and there's a small, very dense nucleus with all the positive charge inside. And there is one experiment that basically proved this, and it was the gold foil experiment, also called the Rutherford-Geiger-Marsden experiment. This is the first thing we will talk about. So, to show you what this experiment actually looks like, there's a source of alpha particles here. Let me use a slightly thicker pen. So this source of alpha particles is normally a radioactive source. They used polonium in the original experiment. And like we learned before, this polonium, as it decays radioactively, it produces alpha particles of roughly, or very similar, or very equal kinetic energies, right? So you can expect the kinetic energies of these alpha particles to be mostly the same. These alpha particles are led through a lead slit, and they go and they hit a gold foil. And the reason they hit a gold foil is because gold is very ductile and can be made very, very thin, right? It can be made as thin as a couple of atoms, or a couple hundred atoms at least. Second reason they use gold is because gold has a very heavy nucleus, or it was a very heavy element, right? And it's assumed to have a very large diameter, right? So when they first thought of this experiment, they weren't expecting the results that they got, right? So what they were expecting was something like this. In the Thomson model, the alpha particle will go right through the atom, right, without a lot of resistance. The positive charges, of course, low density, and the only deflection or change in direction will be caused by the charge difference, the repulsive forces of similar charges. In this case, they predicted that the maximum deflection would be less than 0.02. So they conducted this experiment, and as most of you know right now, you have detectors all around it, right? And actually it's not all around it. This detector is movable in a full circle all around it, so you can detect the angles, right? Every time an alpha particle hits this detector, it shows a small beam of light, and it can be viewed through a microscope. When they did this first here, where they thought most of the alpha particles would hit, and as predicted, a lot of the alpha particles hit here. But as you moved around, there were still particles being detected at other angles, right? So these particles in all these other angles have a very, very few of them, right? So at 10 degrees, they detected about 1 in 1,800 of all the alpha particles released, which is not much. And all the way at 90 degrees, they detected around 1 in 10,000. which you might think, well, isn't that a very small number that can be attributed to uncertainties, right? And the answer is no, because the expected number was 0 at these angles. Anything detected in any quantities would have been deviations from the model. Right. So what actually happened was, the only way this could have happened is if there was something very, very dense in the center of the atom. Right now we know this is the nucleus, right? And because of this nucleus, the alpha particle comes close and can be deflected in large angles that they had detected in the experiment. And in fact, there is, depending on the kinetic energy, right, it's going to be a minimum distance it can get to it. Later, this is defined as the atomic radius. You will learn more about this in the calculations involved in chapter 12.